On January 15, 1919, a giant tank of molasses burst open in Boston's North End. More than 2 million gallons of thick liquid poured out like a tsunami wave, reaching speeds of up to 35 miles per hour. The molasses flooded streets, crushed buildings, and trapped horses in an event that ultimately killed 21 people and injured 150 more. Years later, analysis have pinpointed a handful of factors that combined to make the event so disastrous. Some of those factors included flawed steel, safety oversights, and fluctuating air temperatures. In the background of this picture, you can see the tank that was supposed to be able to hold 2.5 million gallons of molasses. The tank measured 50 feet tall and 90 feet in diameter. The tank was made up of steel and had a wall width of 0.67 inches at the bottom and 0.31 inches at the top.
In regards to the failure of the molasses tank, what engineers did not know at the time was that the steel had been mixed with too little manganese. This lack of manganese gave it a high transition temperature, making the metal brittle when it was cooled below 59 degrees Fahrenheit. The air temperature on the day of the disaster was roughly around 40 degrees Fahrenheit. Its brittleness might have been a final straw leading to the disaster of the tank. Manganese that should have been added would have increased hardenability and tensile strength of the steel used for the construction of the tank. It would have also been able to decrease the critical cooling rate during hardening, thus increasing the steel's hardenability much more efficiently than any other alloying elements. The steel used to construct this molasses tank was surprisingly the same type of steel that was used to construct the Titanic hull plates earlier that century. The composition of the steel can be seen on the screen above. This particular type of steel has a BCC structure which causes it to have a ductile to brittle transition temperature, meaning that at lower temperatures the steel is more prone to a brittle fracture. As seen in the steel composition, there is a low concentration of sulfur, which leads to the metal being more brittle.
One solution would be to increase the width of the walls of the tank. This will increase the tank's ability to withstand the weight of the molasses without breaking. The next would be to choose a steel alloy that has the appropriate properties for the tank. The tank needs to have a high yield strength and have a FCC structure with no ductile to brittle transition temperature. Both properties will allow the tank to withstand the conditions it faced. Having a higher yield strength would allow the tank to be able to support the weight and internal pressure from the molasses. The FCC structure will remove the chance of brittle, failure and increase the ductility of the steel. From the data above, a steel alloy with 14% weight concentration of manganese will provide the highest tensile strength as well as being the most ductile option. Increasing the amount of nickel in the steel composition would allow the toughness of the steel to increase, making it less prone to fracture. Nickel improves the resistance against the corrosion and oxidation at elevated temperatures. Nickel improves the toughness and strength by refining the grain size. Steel alloys with higher nickel compositions are more likely to have an FCC structure, which would make the steel ductile regardless of the temperature. To determine the best steel composition, we need to evaluate the effects of different alloying elements and determine which ones would yield the best results when used in the molasses tank. Copper can increase corrosion resistance and hardness. Manganese can increase high temperature strength, wear resistance, ductility, and hardenability. Nickel can increase corrosion resistance, oxidation resistance, and strength. The data on the far left of the screen shows the properties of manganese steel. The mechanical properties of manganese steels are greatly enhanced by a fine grain size. The typical heat treatment cycle for most manganese steels is shown below the manganese table. This process consists of a solution anneal followed by a water quench. Copper and nickel can both increase corrosion resistance. However, copper increases hardness, whereas nickel increases strength. The addition of copper will not be as beneficial as nickel, since the addition of manganese already increases the hardness of the material. The data on the right of the screen shows the effects of nickel on the tensile strength and the ductility. Based on this data, a steel composition with around 20% weight concentration of nickel would provide the best results for the application. Based off of this information, we have determined the ideal steel composition for this particular usage in the molasses tank. This steel has 0.2% carbon, 0.48% manganese, 0.21% nickel, 0.04% copper, 0.05% sulfur, and 0.02% oxide. On the bottom right of the screen, you can see both the original composition and the adjusted composition directly below the original. This composition has both a higher composition of manganese and nickel to increase the necessary properties for the molasses tank. The microstructure that would yield the best properties would be fine pearlite. This microstructure is achieved by heating the steel to the austenitizing temperature, then holding it at that temperature for the recrystallization stage, and finally allowing the steel to air cool. Fine pearlite has properties that make the material both relatively strong and ductile. In fine pearlite, the layers of ferrite and cementite are layered closely together in comparison to other microstructures. At the top right of the screen, you can see an image of the layers in fine pearlite as well as a drawing that depicts those layers. The boundaries between these layers act as barriers to dislocation movement, which causes deformation of the material. By increasing the number of barriers, the material is less likely to plastically deform and fracture.
Another storage solution is to construct large concrete tanks. One part of this method for storing molasses long-term involves the application of an epoxy layer on the inside of the storage tanks. Because of the high acidity of molasses, the tanks need to have something to deter the corrosive effects of the molasses on the tank itself. These concrete tanks are built with steel panels inside of the concrete walls and into the slab in the ground to provide support and an increased compressive strength of the tank itself.